Hello, adventurers, and welcome to floor 9.5, the balanced hall. A tree leans the way it was planted. It takes a hand the tree cannot feel to set the branches level again, and the line once short stays short. The chart in the next room is the same height as the doorway, and it should not be. You built McCown's catalog last floor as a binary search tree, fast and self-sorting, and then you watched it betray that promise. Feed it names in order, and it grows downward in a single leaning line, a stick, until finding the last beast costs exactly as many questions as reading the old flat list. The rule held, but the speed did not. McCown is here, and he is not at peace with it. He stands before a chart that lists to one side like a ship taking water, and he keeps reaching up to straighten a branch that will not stay straight. Order is not enough, he says. More to the chart than to you. A thing can be perfectly sorted and perfectly slow. Behind him in the dark, above the chair, something moves. A counterweight, a pulley, a hand, and a whole limb of the tree swings up and over and settles, and the chart stands a little straighter than before. The names did not change places in line, only in height. I gave the tree a rule, and it gave me back a list. Do you see it lean? Every name I added was already in order, so every name went right and right and right. And now to reach the bottom, I walked the whole length of it, exactly as I did before I learned to have. Order without balance is a lie I tell myself. But watch the room. There is one move, that lifts a note up and folds its parent down. And when it is done, the same names are in the same order. Left still smaller, and right still larger. Only the tree is shorter. It's what we call a rotation. I cannot do it on every insert by hand. My hands are full of ink. The truly balanced shelves, the ones the next hall is built from, do it for themselves on every single insert and never lean at all. This week, you learn to see the lean and you make the move. Then you go and use that shelf, and use a shelf that never needed you. So we know from what we saw before that the binary search tree works only when it's short. If the height stays near base 2 log of n, so a descent will throw away half the remaining tree at each step. Now, nothing in last floor's code forced that. Balance is the guarantee that is missing. So we need a few things here. One, we need to be able to measure the lean. So a node's balance factor is the height of its left subtree minus the height of its right. So a 0 lean or balance would be level. Far from 0 would be a problem. A tree is height balanced. Okay, this is what we call the AVL property, when every node's balance factor is within plus or minus 1. Now, you may be wondering what AVL stands for. That stands for Adelson, Velsky, and Landis. So, the AVL property, when every node's balance factor is within plus or minus 1. Our sorted stick fails at that root by a mile, and we're going to write a check that proves it. 2, one move re-levels without breaking the rule, when what we call a rotation lifts a child into its parent's place and lowers the parent onto the other side. An in-order walk of the subtree is exactly the same before and after. Left is still smaller, right still larger. Rotation changes height, never order. That is why it is the legal repair, and we're going to write it. And 3 here, we do not build the self-balancing tree. A real AVL tree that applies that rotation at every node on the way back up, every insert and remove, and if you have a secondary rotation needed for zigzagging cases, so it never leans in the first place. There's a lot of code there, and it's already been written, tested, and waiting for you in the standard library. Standard set and standard map are balanced trees. So we're going to measure one against our stick and then not look back from there. Now here we can see a balanced tree versus a stick where we have an issue. So remember, balance is about height, not order. And then we can see here how a rotation can work, where we have a stick here where it's 1, 2, 3. But then if we lift this one up and shift the parent to the other side, you see here we can reduce that height. Okay, so going here into our floor 9.5. So this is a half floor, so it's a little shorter, And the through line through all of this you need to think about is diagnose, repair, don't reinvent the wheel. In the last module, the class built a full binary search tree. Insert, find, in order, the rule of three, and remove. Self-test BST was green. We also proved the catch ourselves. Okay, insert in sorted order, and the tree degenerates into a stick, height of n-1. Lookup falls back to an O of n runtime. So this floor's whole code base is that finished BST plus 5 new stubs in our hero/BST header file. Today we're going to work on our first two, our balanceFactorOf and isBalancedFrom, and these are going to be the tools that we'll use to measure how lopsided a tree is. No new data structure. We are adding instruments to the one we already have. Now, one thing just to be aware of, there are 2 height functions in our BST header file. Our floor 9 height, which counts edges, and of course empty and a single leaf are both 0 there. And then our new provided function called signedHeight, which counts an empty subtree as -1. Okay, so we don't write this, it's given to us, but it's important just to know that it is there. Okay, balance factor needs an empty side to count as 1 less than a leaf, or a 3-node stick wrongly reads as balanced. So a -1 piece there is really important. So let's build this here just real quickly, kind of show where we're at. Okay, and here we'll use this new self-test balance here. You notice here we have a fail. Of course, we have a is balance there's okay. And notice here we have quite a few other fails here. So floor 9 left us with a working tree and an uncomfortable truth here. It's only fast if it's short, and nothing makes it stay short. So look at that last line. Balance claims McCown's catalog is balanced. Factor 0. Okay. Sorry. Okay, yeah. And sorry, I was looking there at the balance factor there, but meaning right here on the last line is balance root. Okay. So that's a lie. We have an issue here right now. The catalog is 6 levels deep on 15 names. It is not balanced. The command lies because the code behind it is actually stubbed at this point. Our balance factor returns 0 for everything. Isbalance returns true for everything. So this module, we're going to make the tree tell the truth about its own shape, and then we fix it. So today we're just going to work on the measurements. So let's open our hero/BST header file, and we will scroll to our new section in that file towards the bottom. Okay. Let's go ahead and find, we should have down here towards the bottom, should have our signed. There we go. So here's our signed height. Now you see this is already filled out for us. But before we write anything, I just want you to see this helper that is provided, because the whole day here hinges on it. We already have height from floor 9. Remember, it counts edges. So an empty tree is 0, single leaf is 0. Signed height is almost identical with one change. An empty subtree returns -1, not 0. Now why does this matter? Balance factor is going to be height of the left minus height of the right. Picture a node with one child, a leaf on the left and nothing on the right. With the edge conventions, both sides read 0, so your balance factor would actually be 0. It would say it's perfectly balanced, but it's not. It leans left by 1. So counting the empty side as -1 fixes that. 0 minus 1, or 0 minus -1, sorry, is 1. So correctly, we say it leans left by 1. Now, here's a trap that can bite you. If you reach for height instead of signed height, when you write balance factor, a 3-node stick will report balance factor 1 and pass the balance check. The exact bug that phase 3 is watching for. So use signed height, and I would say just say -1 for empty out loud as you're kind of rocking and rolling there. Okay, So now let's go down and our balance factor of stub here. Let's go ahead and work on this function. And so on the body here, we want to say if n is equivalent to null pointer, we'll return 0. Otherwise, we're going to return signedHeight. We'll pass in n of left minus signedHeight n of right. Okay, boom, there we go. So 2 lines. A null node leans neither way. So balance factor is 0. That's our guard there. Otherwise, the height of the left subtree minus the height of the right using signedHeight, so an empty side counts as -1. Now, read the sign out loud because it's the vocabulary for the rest of the module here. Positive means the left side is taller, left heavy. Negative means right heavy. 0 means level. On McCown's sorted stick, every real node has nothing on the left and a tall tower on the right. So the balance factor in that case would be a big negative number, as right heavy as it gets. Now let's go down here to our isBalancedFrom. Now we'll say if n is equivalent to null pointer, we'll return true. Otherwise, we'll say const int. I'll say bf is equal to balance factor of, and we'll say n. And then I'll say if bf less than -1 or bf greater than 1, we'll return false. Otherwise, we're going to return isBalancedFrom n of left and isBalancedFrom n of right. Okay. So this is the same recursive shape right here that we've written all stretch. Base case, check this node, recursion to both children. An empty tree is balanced trivially. Otherwise, compute this node's balance factor. If it's outside the range, -1 to +1, the whole tree is not balanced. So we bail out with a false immediately. That's the AVL, acronym I mentioned earlier. That's the AVL invariant. Okay. The rule is a self-balancing tree keeps at every node. And if this node is fine, the tree is balanced only if both subtrees are also balanced. That's the recursive and. One bad node anywhere makes the whole tree unbalanced. Okay. So let's go ahead and build this and see where we're at now. So let's say self-test, balance. So we got a few more. So you see we have a is balanced is good, and our degenerate sorted stick is not balanced. So we see have a few different things there. Also, I can run the I'll go up here. Where am I at? I have the balance command here. Is McCown's catalog tree balanced? So I can say balance. McCown's catalog 15 names, height 6, root balance factor of -3. It is not balanced. Okay. So phases 1, 2, and 3 are green now. So phase 1, balance factor reads 0 on the bushy tree and +1 on the left leaner. Phase 2, the bushy sample is balanced. Phase 3 is the important one here. Okay. The sorted stick of 1 through 6 there now correctly reads, hey, this is not balanced. That phase is floor 9's degeneracy turned into a test that our measurement can finally catch. Phases 4 and 5 still fail. Those are rotations, which will be handled in the second and third videos. And now our balance function here tells the truth. McCown's catalog is height of 6 with a root balance factor of -3. It's lopsided leaning to the right because it's a negative score. This is the same tree as our cold open of the diagram we looked at. The only thing that changed is that the code can now see what was always there. That -3 is the problem the rest of this module exists to fix. Okay. Well, I hope this was a good intro into balancing trees, and we will start tackling those rotations in the next one. Bye-bye now.